Okay, so let's start. So we were talking about some basic concepts in algebra. In particular, we want to set up the arithmetic that we will need to construct error correcting codes, construct, encode, and decode error correcting code. So we discussed the notion of a group and some examples of groups, subgroups, and necessary and sufficient conditions for subsets of the group to form a subgroup. And what is perhaps important for us is this notion of the coset, right? If you have a group and you have a subgroup within it, then the set of all translates of the subgroup form the different cosets. And as we saw earlier, the cosets are essentially tied to syndrome decoding of linear codes. So each syndrome essentially identifies one particular coset of the linear code within f to the power n. Right. So, and once you identify which coset the received vector belongs to, you just identify the nearest code word below corresponding. And we saw that the cosets form a partition of the group within this group itself. All the translates are disjoint. They all have the same size, and they form a partition of G. This essentially implies that given a particular group, any subgroup can't have an arbitrary size. If n is the order of a group G and H is any subgroup, then the size of H must divide n. In particular, if G is a group with prime size, then it implies that it can only have the trivial subgroups as subgroups, right? Itself and the group containing only the zero element. You can't have any non-trivial subgroup, right? But then we're interested in not just addition and subtraction. So groups only allow us to do addition and subtraction, nothing more. But now we want some more operations, right? And for that we need this notion of multiplication and division. And we're thinking about how to generalize this from the set of integers to arbitrary subgroups. So the minimum set, at least the minimum set of operations that you need, or the minimum algebraic structure that you require in a set, is basically the ring structure. So of course, if you have a field, then you can do all kinds of operations: addition, multiplication, division. It's closed under division as well. But it's okay if some sets are not closed under division. So for example, if you look at the set of integers, the set of all integers is not closed under division, right? If I take 2 by 3, then this is not an integer. But then there is still a well-defined notion of division. Basically, Euclid's algorithm says that you can divide. You can basically try to divide one integer by another, but maybe not exactly. So, in particular, if you go back to your primary and high school arithmetic, then given any two integers, you can always write one integer as a times some quotient plus a remainder. Right? And we want to do this for more general sets. So, for example, can we do this over maybe the set of polynomials? Right? If a and b are polynomials, then is there a well-defined notion of this Euclid's division algorithm? So those are the kinds of questions that we want to address. So what is a ring? A ring is basically a set with two operations. It's like a field, but it doesn't have so many properties associated with it. So every field is a ring, but not every ring is a field. For example, so what are the properties that ring has to satisfy? Firstly, under addition, it should form a group, and this multiplication operation is such that it is associative. There exists a multiplicative identity, and there's distributivity. Right? This is all that we require. We don't require every element to have an inverse. So the set of integers certainly forms a ring. So the set of integers is a ring. But more importantly, we are interested in the polynomial ring, that is the set of all polynomials. So, given any field, the ring of polynomials is defined as follows. So we'll use this f and x within square brackets. So this is basically the set of all polynomials with coefficients from set of all summation I equal to 0 to m ai x raised to I, where all the ai's come from f and m is finite. But m can be arbitrary, it need not be fixed. I'm not fixing m at the moment. So set of all, so a0, a1, x1, a0 plus a1, x1 plus, and also a0 plus a1, x1 plus a2, x square. So, and is it obvious that this is a ring? Firstly, is it a group? So what properties do you have to check? Is it closed? Firstly, under addition and multiplication. So sum of two polynomials is another polynomial, and product of two polynomials is also another polynomial. And all the coefficients come from some field. So addition and multiplication therefore is well defined. So it is closed. So it's closed under multiplication and addition. What else do we need to check? What is the additive identity? So it's basically the zero polynomial. The zero. What about the multiplicative identity? One, the unit element in the. Whatever the identity of the field is, that itself is the multiplicative identity. Okay, what else do we need to check? Additive inverses. So if a of x is a0 plus a1x so on plus amx power m, so it's a degree m polynomial, then what is the additive inverse? Yeah, so basically take the additive inverse of each of the coefficients. A0 bar plus a1 bar x x to the power. What else? Associativity. Both addition and multiplication is associative. Anything else? Closure under multiplication. Well, you have to be sure that the product of whatever two objects is also lies within the set, right? Correct. But sure. Here the again I have not explicit spelled it out, but both addition and whatever these two operators are, they should be closed. So the set should be closed under both these operations. Distributivity, and that is right. Any questions? Sure. No. So the assumption. Okay. So here, of course, perhaps I should add that so it is closed under multiplication. You can give me an example of a set which forms a group but not a ring. I mean any set. So let's assume that yeah, maybe one of these properties should not be satisfied. Set of all 2 by 2 matrices. Okay. Why does which property does it violate? Multiplication is associative. Is it possible to look at a subset of the set of all integers? set of, but does that form a group? Yeah, set of all even integers. So it forms a group. Which property is not satisfied? Multiplicate. There's no multiplicative identity. So, 2z, yeah, is a group, but not a ring. Okay, so now essentially we want to mimic what we were doing for integers, right? For example, Euclid's division algorithm. Correct. So let's see if we can do something similar. So what does Euclid's what exactly is Euclid's algorithm do? So basically, given any two integers, a comma b, maybe 10 and 20, we can always write b equal to a times q plus r, where q is again an integer and r is greater than or equal to 0 but strictly less than a. Correct. Uh, so what exactly can we infer from this? So look at b. So b is in the group of integers, right? So one way to look at this is in the following way. Let us look at a times z, right? So a times z is a subgroup of z, right? Uh, One way of stating this particular thing, b equal to aq plus r, is to say that b is in a times z plus r for some 0 less than r less than a. Correct? And one way to sort of give a proof of this statement, that given any a comma b, you can always write b equal to aq plus r, is to simply observe that az plus 1, az plus 2, 1, az plus a minus 1, these are precisely the cosets of az. Right? So these form a partition of z. So given any integer b, b will obviously lie in one of these cosets. Correct? And the more importantly, we're using some specific coset representatives. That is, the set of all coset representatives are those between 0 and a, or 0 and a minus 1. So this is sort of a group theoretic interpretation of this particular statement. So now, given any ring, right? Take any ring. For example, consider the set of all polynomials. Okay? And take some polynomial. Okay, maybe it is x square plus 2x plus 1. Okay? And now look at the set of all multiples of x square plus 2x plus 1. So x square plus x plus 1 times f of x. Or in other words, a set of all polynomials which are which this particular polynomial divides. One way to look at it. Just as we had the set of even integers, which is the set of all integers which can be divided by 2. This is the set of all polynomials which can be divided by x square plus 2x plus 1. So this forms a subgroup of f of x. Do you agree? Because if I add two elements, right, the x square plus 2x plus 1 divides the sum of two elements within this. If I multiply this by another element, it still is divided by x square plus 2x plus 1. So a of x times f of x is a subgroup of f of x. Correct? Okay. So now what do you think are going to be the various cosets? Yeah? Agreed? Yeah? Huh? So we are basically looking at coset representatives, right? Okay. What is one set of coset representatives? Set of all polynomials with degree. So these will be the cosets with the degree of A. Okay, do you think this is, why do you feel this is enough? If alpha of x is x square, what is the problem? Correct. Okay. Okay. We haven't gone into reminders yet, right? So sure, the one way to think of it is as the remainder. Yeah. Correct. Okay. Why can't you divide it? So what? That's a polynomial with a smaller degree, right? Yeah. So, so therefore it suffices to take the set of all polynomials with degree less than the degree of, in this case, less than 2. So the for the coset representatives, it is enough to take all those polynomials whose degree is strictly less than 2. Right? Another way of stating this is, given any polynomials a of x and b of x, we can always write b of x as a of x times q of x plus r of x, where this is our quotient, this is our remainder, and the degree of r of x is strictly less than the degree of a of x. Yeah. Then I can further divide, right, to give something of smaller degree. But once it is less, there's nothing more I can do. So I keep dividing until the degree is strictly less than the degree of a of x. If it is not less than a of x, then I can further divide. So I can proceed in an inductive fashion. So maybe let's just take an example, right? Take a of x is equal to x squared plus 1, b of x to be x to the 4 plus x plus, okay? And the coefficients come from f2. So these are the coefficients are not real but binary. Okay? I want to find the quotient and the remainder. So if you remember the long division method, x to the 4 plus x plus 1, I'm dividing by x square plus 1. So what would I first multiply it by? I multiply it by x square. So at every step I want to decrease the degree by at least 1. So multiply by x square, I'll get x to the 4 plus x square. I subtract this out, so it is 0 plus x square. It's minus x square, but minus x square is the same as x square, plus x plus 1. Can I degree, is the degree less than the degree of a of x? Not yet. So I can multiply by what? 1 to get x square plus x, 0 plus 0 plus 1. So the quotient is x square plus 1 and the remainder is 1. Right? So I can write x to the 4 plus x plus 1 as x square plus 1 times x square plus 1 plus 1. Sorry? Okay. Should be plus 1 x. Correct? Any questions? Yeah, any question? So there is this notion of one element dividing another, right? Just like in the integers, we know that 2 divides 4 and 2 divides 6. Just like that, we have this notion of divisibility over polynomials. So, so we say that a of x divides b of x. Basically, if the remainder is always equal to 0. If there exists some polynomial q of x such that p of x can be written as a of x times q of x. If you look at our previous example, this a of x does not divide b of x because the remainder is not equal to 0. Right? So in the integers, we also had this notion of common divisors. So given any two integers, any integer which divides both is a common divisor. And with that, you also saw what the greatest common divisor was. It is the largest integer which divides both integers. So the GCD, the greatest common divisor of any two polynomials, a of x and b of x, we define to be this to be the polynomial of largest degree which divides both a of x and b of x. But unlike the integers, in this case, the GCD is not unique. Can you tell me why? Oh, suppose I give you one GCD. I want you to be able to construct another GCD which is different from this, so a different polynomial which divides both a of x and b of x. Okay, let's take an example. So let us say a of x is a x square plus x, and b of x is, let's say, x square plus 2x. What is the GCD of these two? Yeah, x. So x divides x square plus x. X also divides x square plus 2x. Let's assume that the field is the field of reals, reals, real numbers. So x is a GCD. Is there any other GCD? X by 2. Right? So any scalar multiple of a GCD is also a GCD. So basically, so x square plus x divided by x is x plus 1, right? And x square plus x square plus 2x divided by x is x plus 2. Okay? But if I divide these two, if I divide these by x by 2, then this is just 2x plus 2 and 2x plus 4, which are still polynomials. So every scalar multiple is also a valid polynomial. It's a valid GCD. So GCD is unique up to scalar multiples. Okay? But absolutely it is not unique. One way to sort of resolve this issue is to force maybe the coefficient of highest degree term to always be equal to 1. Right? So in this case, if I said that the coefficient of the highest degree term, which is x in this case, should always be 1, then the GCD is unique. It has to be x. X by 2 is not a valid GCD because the coefficient of the leading term is not equal to 1. But will we lose about this and say that okay, GCD is unique but up to scalar coefficient? Okay. Now, okay, so we know that the GCD is well defined, but how do we actually find the GCD? If I give you two integers, how do you calculate the GCD of these two integers? How will you do it? So you're going to look at all possible primes less than this, divide, and then go on. If I give you, yeah, how do you do that? Yeah. Okay. You will find all the prime factors and then go on. Okay, but is there a better way of doing it? Okay. Okay, so let's take, give me two numbers. Say 2, 3, 0, 69 and no, 3 is too small. Give me something bigger. 69 and 63. Well, okay, 69 and 63. Okay, so let's divide. This is again a little too small, but can you give me something, let's say, what, something which it's a multiple of 3. Okay, fine, 33. So you take 69, divided this by 33, 36, gives me 3. And then I'll take this number over here, try to divide 33 by 3, 33. So if I end up with, I keep proceeding this way, I'll divide the bigger, first divide the bigger number by the smaller number, find out the remainder, and I'll divide this divisor, by the remainder, and I keep proceeding this. Keep proceeding till I get a 0. The last non-zero remainder is going to be the GCD. Okay. So let's do this for polynomials. So take a of x to be x power 4 plus square plus x plus 1, and maybe b of x is x cubed plus 1. So what's the first step? I multiply x cubed plus 1 with x. I get x to the 4 plus x. What is the remainder from the first step? X square plus 1. Okay, is the degree less than this? Yes. So I can't divide any further. I'll bring x cubed plus 1 here. X cubed plus x. The remainder is x plus 1. Square plus 1 plus x. X plus 1. Can I divide further? So what is the GCD? It is x plus 1. So let's just check. Sanity check. Does x plus 1 divide x cubed plus 1? What is the x cubed plus divided by plus 1 is going to be x square plus x. We are doing our F2. F2. Yeah, unless otherwise mentioned, the field is always going to be F2. It is not over the reals. Okay, and does it divide x to the 4 plus x square plus x plus 1? is x cube plus okay. So all right. So why am I going about all of these? I'm kind of revisiting high school math, but now I'm of course something new is that we're doing this over polynomials and not just over integers. What is the purpose? Let's think back uh, when we discussed prime fields. So we had this notion of primes, and we saw that the set of integers modulo a prime forms a field. Right? So now we had the set of integers, which was a ring, and the set of integers modulo a prime number gave you a field. But then if I took it modulo some other integer, which was not a prime, then I didn't end up with a field. We saw that inverses didn't exist. Right? And one of the main reasons why inverses exist was because the number p, whatever you took modulo, that was a prime. If the main issue that you have if p is not a prime is that all those integers which divide p, those integers will not have inverses, and that can be resolved by taking p to be a prime. We want to do something similar here. So we have the set of polynomials which forms a ring. It doesn't form a field, right? Because inverses don't exist. So we don't have the inverse for x plus 1 or x square plus 1. But now the way we'll proceed is by taking the set of all polynomials modulo some other polynomial. And for that I need this notion of whatever prime polynomials, whatever is equivalent of prime numbers over the integers. And what is the definition of a prime number in the set of integers? Yeah, so the only numbers which divide that particular number are 1 and itself. Similarly, I'll want a similar, I'll have a notion of being prime, but here it's not called prime but irreducible. So we'll say that a polynomial is irreducible if basically the following happens: p of x divides a of x only for p of x being a constant, or the other way to put it, so this implies that degree of p of x equal to 0, so it's a constant, or p of x is some constant times a of x. Another way to put this is that degree of p of x equal to degree a. So it doesn't have any non-trivial divisors. So this is the generalization of prime numbers. So if I take any two integers, of which one is a prime, what can you say about the GCD? Or it's always 1, right? Correct, that is right. So it's 1 or the prime number itself. So So given any two polynomials, a of x and b of x, what can we say happens when the GCD of the two polynomials equal to 1? This implies a necessary and sufficient condition for the GCD of any two integers or any two polynomials being equal to 1 is that you can find other integers alpha of x, beta of x, such that a of x alpha of x plus b of x beta of x equal to 1. Have you seen such a statement before? So the integer version is the following. So given any two integers a comma b, you can always find integers c and d such that a times c plus b times d is equal to the GCD of a and b. Okay. Have you ever seen this before? You may or may not have. Right. And this is easy to get from this. So let's go back to this. So we use the sort of long division method to find the GCD of two numbers, right? So let us write this down. Okay. What can we say about 33? So, or maybe let's start at the top. What did we say about 69? So 69. Okay, let's start. So we have that this number, the GCD, is going to be the last remainder in the entire process. Correct? So I can write 3 as, so this is the remainder of this particular operation. Right? So this is equal to 69 minus 33 into 2, or this is equal to 69 into 1 plus 33 into minus 2, which is, so in this case a equal to 69, b equal to 33, c equal to 1 and d equal to minus 2. So this was a trivial case. Now let's look at this particular example, because at least there were like 2 steps involved here. So what do we have over here? This is the last remainder. This is the GCD x plus 1. How can we express x plus 1? So x plus 1 is equal to x cube minus 1, x cube plus 1 minus x into x square plus 1. X plus 1 is equal to x cube plus 1 minus, or in this case, since we're operating over the binary field, plus x square plus 1 times x, right? Okay, so we have x cube plus 1. Let's leave it as it is. Now which is the remainder over here? It is x square plus 1. Now I'll again rewrite this remainder in terms of the dividend, divisor and the quotient. This is x cube plus 1 plus x square plus 1 is this polynomial minus this polynomial into this. Right? So it is x to the 4 plus x square plus x plus 1 minus x into x cube plus 1 times x. So it is x cube plus 1 plus, so I have another x cube plus 1 term over here, and the coefficient is basically x into x, which is x square, so this is 1 plus x square plus x to the 4 plus x square plus x times x. So by iteratively writing the remainder, remember that the GCD was the final remainder in this long division process. So I can always write the remainder as whatever this term minus this into this. I'll again rewrite the remainder as this minus this into this, and I can keep proceeding. And it's intuitively clear why I will finally end up with one of the polynomials times some other polynomial plus the other polynomial times, correct? Any questions? Yeah. See here definition. Huh? Correct. In this case, we're just saying it's not exactly a one-to-one mapping. Okay. So for polynomials, we're defining this is the intuitive equivalent of prime numbers. So I define the polynomial to be irreducible if the only divisors are constants and scalar multiples of itself. That's it. There can't be any other polynomial of degree greater than 0 but less than the degree of itself and also divides this polynomial. So that's the definition of an irreducible polynomial. So okay, so let's look at, can you give me some examples of irreducible polynomials? Take a field. Let's take the field of real numbers. Can you give me some irreducible polynomials? What about constants? Are they irreducible polynomials? They are, trivially. Any other irreducible polynomials? Okay, x plus 1. Any scalar multiple of, so x plus alpha. So all degree 1 polynomials irreducible? Wait, so let's try to answer this question first. Are all degree 1 polynomials irreducible? Yes, no? Yes. Why? Correct. So, therefore, there's nothing in between. All degree 1 polynomials. Okay. What about degree 2 polynomials? Is there a degree 2 irreducible polynomial? X square plus x plus 1. Why is that? Okay. Can you give an even simpler example? X square plus 1. This is an irreducible polynomial. So, any polynomial whose roots are strictly complex is basically an irreducible. Well, it's not strictly true. So let's look at polynomials of degree 3. Is it possible to find an irreducible polynomial of degree 3? Yeah. Yeah. If we have it. Yeah. Yeah. Should have at least one real root. So it's impossible to find any. So in the set of reals, there are no cubic irreducible polynomials. Yeah, for the real field. Okay. What about degree 4? Is that irreducible? Is not, right? Yeah. X power 4 plus 1. Are you sure? What can you say about the roots of any degree 4 polynomial? What is any degree polynomial? The roots are real or they're complex? If they are complex, what happens? Okay, fine. Suppose there is one complex root. What can you say? Can you say something about any other root? Complex? Just complex or something special? It should be the complex conjugate. What can you say about, so let's say that A is the complex root. So A star is the complex conjugate. What about x minus A into x minus A star? Yeah, yeah. And what property does that have? No, it's not x square plus A square. Wait, minus. A is a root of, let's say, f of x, x A, okay, which is what? But what can you say about this? What kind of a polynomial is this? The coefficients are real, right? Correct. And what about f of x divided by x square minus a square? Is that going to have real coefficients or non-real imaginary coefficients? Yeah. My claim is that f of x divided by x square minus mod a square is going to be real. It's a real polynomial. Why? As long as degree of f of x is greater than 2. Yeah, I mean, even otherwise, even if it is 2, it's a constant. Okay, I have f of x. I know that a and a star are the two roots, of f of x. Correct? I want to know if this polynomial divides f of x or not. My claim is yes, it does. So f of x divided by x square minus mod a square is a polynomial with real coefficients. Why? That is okay. So yes, correct, correct, yes, yeah, yeah, okay, okay, yes, yes. So what is one way of writing any f of x? Yeah, it's a product of. So you can write it as x square minus mod a1 square times x square minus mod a2 square, so on. Suppose it has 2m complex roots, x square minus mod am square times, it has some real roots, x minus alpha 1 times x 2, and all of these are divisors. And this is true for all polynomials of degree at least 2. So can there exist irreducible polynomials of degree greater than 2? There can't. So every irreducible polynomial has to have degree at most. That's a property of the reals. And we'll see a little later on when we see how to construct fields from polynomials that the set of complex numbers can be constructed from the set of reals. The field of complex numbers can be constructed from the field of real numbers using a particular mechanism. And you can describe that using polynomials itself. So there's an algebraic description of the field of complex numbers using the field of using the ring of polynomials. Correct. So one way is to bring this imaginary number, right? But there's a more systematic way of constructing the field of complex numbers from the field of real numbers. Okay. So let's take another example. What about the binary field? What are the irreducible polynomials? So obviously x and x plus 1 degree 1 polynomials are always irreducible. What else? What about degree 2 polynomials? Is x square irreducible? Sorry? So x square is not irreducible. What about x square plus 1? Okay. Remember, it's the binary field. X plus 1 into x plus 1 gives you x square plus 1. Basically x square plus x 1, but x plus x is 0. So x square plus 1 is not irreducible. What else? Any other polynomials? X square plus x? Yeah? Exactly. Then what else? No irreducible polynomials of degree 2? Yeah? X square plus x plus 1. Is it irreducible? Does x divide this? No. Does x plus 1 divide this? Does x plus 1 divide x square plus x plus 1? It doesn't. So this is the only irreducible polynomial of degree 2. Uh, Similarly, you can so clearly there exists at least one degree 2 irreducible polynomial. Not every degree 2 polynomial is irreducible. Similarly, for each degree, you can find an irreducible polynomial. So for 3, it turns out that you can check that x cube plus x plus 1 is irreducible, and x cube plus x square plus 1 is irreducible. X cube plus 1 is not irreducible, as I think we just discussed earlier. Correct? So a useful property, it's not at all obvious and it requires a very deep proof, is that for every degree m, I can always find an irreducible polynomial of degree m for the binary field, or in general for every finite field. If I take a finite field, or say any prime field, and look at the for any fp, p a prime, and any positive integer m, you can always find an irreducible polynomial degree m in fp of x. We will not discuss the proof of this because that requires a lot of theory to just get to this particular point, but we'll assume that yes, this is true. It's not easy to just write it down. You can it's possible to find out the number of irreducible polynomials also, but yeah, you have to check. Which, no, there are multiple. In general, there are multiple irreducible polynomials of degree n for finite fields. For prime fields, coefficients from prime fields specifically. Okay, so maybe I should. So perhaps let's stop here. It's a logical stopping point. Okay, so quickly, we've seen how to find the GCD of two numbers or any two polynomials, right? And more importantly, we know that, at least I have claimed that given any two polynomials, if the GCD is equal to 1, then you can find some other polynomials alpha of x and beta of x, such that alpha of x a times a of x alpha of x plus b of x beta of x is equal to 1. Similarly, for any polynomials a and b, you can find polynomials c and d such that ac plus bd equal to the GCD. But one other point here is that if you can find polynomials alpha of x and beta of x such that a times alpha plus b times beta equal to 1, then it necessarily implies that the GCD is equal to 1. Okay, that's a surprising result, but we will prove this. We'll prove both, that if the GCD is equal to 1, then this is true. If this is true, then the GCD is equal to 1. This basically follows from this, right? Okay, so let's stop here. Any questions? So ultimately, we'll see that to construct any possible finite field. One way is to either look directly as that is, you just look at the field of integers modulo p. But we see that for if you want to construct other kinds of finite fields, then the algebraic structure is essentially the same as the structure of the set of all polynomials modulo some other polynomial. So if you want to implement say a linear code over a field which is not having prime size, then we'll have to do polynomial arithmetic. Okay, so let's stop here.